So now that we've talked more about scatter plots and just what to expect, we'll dive into actually looking at an equation of a line for a stochastic model here for our statistics data. So first, just a reminder what the equation of a line looks like. Our typical algebra equation is that y equals mx plus b, where b is what is called our y-intercept, and m is our slope. So we're still going to have the same idea of coming up with this equation of a line, but if you recall, when no longer all the points are falling on a line, it's a little bit harder to figure out, well, what is that exact equation? So we're going to talk about how we find that equation. So first, let's look at this graph. Here, we're trying to predict the number of trick-or-treaters at someone's house based upon the population density in that area. So you could use some type of straight edge here and try to put a line that you think fits the data the best. Now, although we might not all have the exact same line on our graph, I would expect that we all have something that has a positive slope going on here with it. Now, why would you have put the line on the graph where you did? So for example, why would your line maybe look something like that instead of something like that? So probably what we're trying to do is sort of split the data right down the middle and kind of be going right down the middle of that entire data set the entire time that we're going. So maybe a question to think about is there a correct line? Well, technically speaking, there are different methods to create a line. And depending upon what method you use, you can actually get a different equation of a line. So the method we are going to talk about is what's called least squares regression. So here is an understanding of what must happen for this. So there's one point that the line must go through. It is going to go through the point of the sample mean of x bar and the sample mean of y bar. So that is going back up to our picture here. If I took all of these points and just looked at their population density, and I found their average population density, then if I looked at the number of trick-or-treaters and found the average number of trick-or-treaters, it's going to have to go to that point that finds my average of all of them, which may be, for example, about right there on my graph. So it must go through that point. Then, under that restriction, it's going to minimize the distance from each point to the line. Keep in mind again that there's this point that it has to go through, so it's going to be trying to, using that sort of as your pivot, kind of think of it like a teeter-totter of where you'd have to be, and trying to sort of move this teeter-totter that it's close to every single point that it can be at the same time. Now, we're not going to actually do this math by hand. We're going to understand its process instead. So first, let's just talk through what the equation is going to look like. So our equation is going to be that y hat is equal to mx plus b. So this is very similar to the equation that we've already seen for a line back in algebra class, but the main difference is that on this y, I have this hat. So let's actually first talk about what this y hat is even supposed to mean. So y hat is your predicted value of y. And just for comparison, if I actually use the letter y, what y would represent for something is the actual observed value. So for example, I might predict what your exam 3 score is going to be. So I would have a predicted value, a y hat. But then when you actually take the test, you're going to have an observed value of y. So those could be the same, but they could also be different. So I want to use a different symbol to say what was predicted to happen versus what actually happened. Now B, we would say, is our y-intercept, but we're also going to talk about what that means to be a y-intercept. So B is the expected value of y when x is 0. Right, that's where we cross the y-axis, so that means that x is 0. And m, which is our slope, is our expected change in y, which could be an increase or a decrease, when x increases or goes up by 1 unit. And so we're going to be doing a lot of interpreting of these values. We will not be calculating the slope and intercept, but I will also show you what the equations look like. 1, to have you appreciate that we're not doing them by hand, but 2, to understand the idea of what's going on. So for the slope, this m, remember this capital sigma that I'm going to be writing just means to sum or to add things up. And this sum would be done for as many values as I actually have in my data set. So basically for every individual point on this graph, I would have to do this math. So that's why we're not doing it by hand. Then I'm going to see how far my value of x is from its mean times how far my value is of y is from its mean over the sum of this x distance squared. Now, the reason why I show you this formula is slope, because it can be positive, it can be negative, or it could be 0. And so when I get a positive slope, this is going to have to happen in the top value because the bottom number is going to always be positive. So the top is going to have to be positive. In order to be negative, this top is going to have to be negative. And to be 0, this top is going to have to turn out to be 0. So trying to understand this from a picture perspective here. So suppose I have data that looks like this. So I would expect to see a positive slope for my graph. So what I'm going to do is find out about where my sample mean of x bar is and where my sample mean of y bar is. And based upon where these values cross, I can kind of see I got these different quadrants. So values that are up here are above both the sample means. So I'm going to get a positive times a positive, which will give me a positive. All the values down here are below each of the sample means. So I would get a negative times a negative, which will also give me a positive. The values in the other two quadrants are going to give me negative values on this top part. So as you can see, if you have a positive slope, most of the points are going to be in those two quadrants. And if you had a negative slope, most of the values would be in those two quadrants. But again, we're not going to calculate this. That was mainly for understanding. What we will be doing is interpreting this. And for slope, we will always interpret this value. Now, moving on to the intercept. Now for the intercept, to find that value, it's a little bit easier. It just involves the two individual sample means as well as our slope. So the intercept is affected by the slope, and that's probably the main thing to really understand about it. Now when it comes to the intercept, we may interpret it. We have to actually check before interpreting. So there's going to be 3 questions that we're going to ask before we actually interpret it. The first question is we're going to ask if x equals 0 makes sense to us or not. Because the intercept is the predicted value of y when x is 0. So we're going to first see if x equals 0 even makes sense. Secondly, since it would be then the value of y, so could y actually be close to equaling this value of b? And finally, if we have any data near x equals 0. So sort of going back to some of the questions we've talked about previously. So first understand the can x equal 0. So could I miss 0 classes? Yes, that makes perfect sense. Could I have a house of 0 square feet? No, so that doesn't really make sense for me to look at then. Now for the second question, we would actually have to know what our intercept is to see if that value would make sense. And we'd actually have to see a scatter plot of our data to see if the last one makes sense. So for example, for the any data near x equals 0, if I were to look at this plot, my population density is my x. If I actually look, notice this is actually not the point 0, 0, because this is going in equal distance of 500. So this maybe is about 1,000. So 0 is probably really way out here. So that's where we have to be careful, is that this value is not always going to be that 0, 0 spot as well. Finally, before we get into an example, I want to talk about what things are called residuals. So residuals are necessary because not all of the points will perfectly be on the line. So that's why we're going to have this thing called residuals. Sometimes people call them errors as well. I prefer to use the word residuals. That way it doesn't sound so negative, for example. So this is the math formula behind it. So it's y minus y hat gives us this e, or that residual. Or another way to think of it is your observed value, what actually happened, subtracted off by your predicted value. So this really kind of measures how far off our prediction was from what really happened. And so we can get a positive number, a negative number, or 0 when we do this calculation. And if we get a positive, that just means your observed value was bigger than your predicted value. Visually, this would be a point that's above the line. If you get a negative, that just means the opposite is true, that your observed is smaller than your predicted value, which this would be a point that falls below the line. And finally, if you actually had a value of 0, that would mean that the two values equaled each other. This would be a point that's actually on the line. So if you think for a moment as my red line here being the correct line, all the points here above the line are going to have a positive residual because their observed value was higher than their predicted value. All the points below the line would have a negative residual because they had a smaller observed value than what I would have predicted. And then any point that falls perfectly on this line would have a residual of 0 because I perfectly predicted what would happen. Now the goal in the next video is to try to apply this to an actual problem. So I would recommend going ahead and watching that video while this idea is still in your head well.